Since the introduction of scanning electrochemical microscopy, or SECM, in 1989 and its commercialization in the 1990s, its use has grown sharply, making it the most popular form of scanning probe electrochemistry. This popularity has seen SECM used in fields as diverse as batteries, biology, and corrosion. During this video presentation, we will introduce SECM in its many forms and its use on BioLogic's M470 scanning electrochemical workstation. This presentation is broken into two parts. In the first part, the SECM 470 will be covered. This module is capable of constant height DC and ac-SECM. We will discuss the principles of DC and ac-SECM, introduce their use on the M470, and finally look at the results from the test sample using DC and ac-SECM on the M470. In the second part, we will focus on the ic-SECM 470, the constant distance module of the instrument. The ic-SECM 470 module can be used with both DC and ac-SECM. We'll cover the principles of this technique, how it is implemented on the M470, and the results which can be obtained by measuring the test sample with ic-SECM. Let's first look at the DC and ac-SECM techniques. First, dc-SECM. A key component of SECM is the Ultramicroelectrode, or UME, which acts as the probe. The UME is polished flat, resulting in an inlaid disc at which hemispherical diffusion occurs. When steady state is reached, the current is diffusion limited and defined by the equation shown. In this equation, N is the number of electrons transferred, F the Faraday constant, D the diffusion coefficient, and R the electrode radius, all of which can be considered as constant. C star is the bulk concentration, which will be shown in the next slide as the variable causing the steady state current to change in SECM. By far the most common mode of dc-SECM is feedback mode. In this mode, the probe is biased to interact with the redox mediator specifically added to solution for the measurement. The sample is not biased and is often not connected to a potentiostat. When the probe is far from the surface, hemispherical diffusion occurs and the bulk current is measured. When the probe is near a conductor or sample active towards the redox mediator, the sample regenerates the redox mediator after it has interacted with the biased probe. This causes the concentration of the redox mediator available to the probe to be higher near to a conductor than when it is in bulk. The result is a measured current larger over a conductor than in bulk solution. When the probe is instead near an insulating or inactive sample, the diffusion of the redox mediator to the probe is blocked. This causes the concentration of mediator available to the probe to be lower over an insulator than in bulk solution. The result is a lower current measured over an insulator. An important experiment type in feedback mode SECM is the approach curve. As the probe approaches the sample, the current measured changes based on the probe to sample distance and sample type. When the probe is approached towards a conductor, as the probe to sample distance decreases, the current signal increases exponentially. This is referred to as positive feedback. If the probe is instead approached towards an insulator, as the probe to sample distance decreases, the current signal decays exponentially. This is referred to as negative feedback. When the approach curves to an insulator and conductor are overlaid, we can see that the signal measured by the probe is affected by the changes in surface conductivity and topography. Here we see that as the probe moves down, or it moves to a higher surface, an exponential change in signal is expected. If the probe instead moves between areas of different activity, the signal will change. In this case, moving from an insulator to a conductor will cause the signal to increase. What does all of this mean for a feedback mode experiment? The result is that in feedback mode there are two types of contrast: sample activity and sample topography. If we first consider a completely flat sample with varying activity, the measured signal will depend only on the activity. High currents would be from features with high activity, and low currents from features with low activity. If instead the sample is completely insulating, but with varying topography, the signal will depend only on topography. High currents would be measured at dips in topography, and low currents at high topography features. Real samples with topography and activity variation will produce signals influenced by both. As the most common form of SECM, feedback mode has been used in most application areas in which bulk electrochemistry has been used. Feedback mode is useful for measuring flat samples. Because the sample does not need to be biased, feedback mode is particularly useful for measuring samples with conducting regions isolated in large insulating regions. These could be difficult to measure by other means. The next most common mode is generation collection mode. In this mode, the redox mediator of interest is generated during the experiment. There are two types of generation collection mode. The most common form is substrate generation tip collection mode, in which the tip is biased to interact with a mediator generated by the sample. The sample may be freely active and generate the mediator in this way, or it may be connected to a potentiostat and biased to generate the mediator. Less common is the tip generator sample collector mode, in which the sample is biased to interact with the redox species generated by the tip. Substrate generator tip collector mode is particularly useful in the measurement of concentration profiles and the flux of electrochemical species during a reaction. This mode has found use in the study of corrosion, enzymes, and catalysis. The final mode we will discuss is competition mode. In this case, the probe and the sample compete to interact with the same mediator in solution. The sample may be naturally active towards the mediator, or it may be biased to take part in the same redox reaction as the probe. When the probe is over an active area of the sample, there is less or no mediator available to interact with the probe. This causes a decrease in the measured current. Competition mode is particularly useful to measure the local ability of a substrate to interact with a redox mediator. As such, it is used in catalysis and corrosion studies. With this background knowledge of dc-SECM, we can now look at ac-SECM. What happens if you cannot use a redox mediator? This is the case when the mediator adversely affects the system under study, meaning it does not necessarily reflect the real-world situation. For example, when living samples are of interest, redox mediators can be toxic to these samples. On the other hand, when corrosion samples are measured, using a redox mediator can enhance or inhibit the corrosion. In these cases, can you still use SECM? The answer is yes. For these samples, ac-SECM, which can be performed without a redox mediator, can be used. In ac-SECM, a sine wave signal is applied to the probe, allowing the sample impedance to be locally measured. As with dc-SECM, the sample material affects the signal measured by the probe. While for dc-SECM there are only two possibilities, there are three possibilities in ac-SECM. In all cases, when the probe is over an insulator, the signal path from the working electrode to the counter electrode is always through solution. As the probe to sample distance decreases, the layer of solution between the two decreases. This therefore causes impedance magnitude to increase, as illustrated. For a conductive sample, there are two possibilities with decreasing probe to sample distance. If the measurement is performed in a high conductivity electrolyte, for example seawater analog, or low measurement frequency is used, then the most likely signal path from the probe to the counter electrode is through solution. In this case, therefore, the behavior is similar to that at an insulator. As the probe to sample distance decreases and the solution layer becomes thinner, an increase in impedance is measured. It should be noted that although the behavior is similar for both the insulator and conductor, in this case the impedance will often be lower over the conductor than over the insulator because a path through the sample does exist, although it is not favored. When a conductive material is measured in a low conductivity electrolyte, for example tap water, or at high frequency, it is now favorable for the signal to short through the sample. Therefore, as the decreasing probe-to-sample distance causes the solution layer to become thinner, the barrier to the signal traveling through the sample reduces. This in turn causes the measured impedance to decrease, as illustrated. To summarize, when an insulating sample is measured, it will always result in an increase in impedance. When a conductive sample is measured, the result is dependent on the electrolyte and frequency used. At low frequencies and high electrolyte conductivities, an increase in impedance will be measured. While at high frequencies and low electrolyte conductivities, the impedance will be lower over a conductive sample. There are two consequences to using ac-SECM. The first is that a mediator is not used, which can be beneficial if a good mediator cannot be found. The second is that users can tune their experiment by changing the measurement frequency and/or the electrolyte used. So how is SECM implemented on the M470? dc-SECM and ac-SECM use the same configuration of the M470. The control PC contains the M470 software, which interfaces with the equipment to set up and run the experiment. There is an XYZ stage, allowing for precise movement of the Ultramicroelectrode probe in all three directions. A small volume cell with the possibility of sample leveling is used. Depending on the SECM experiment, both the probe and the sample may need to be biased. Therefore, the M470 is integrated with a bipotentiostat, which is EIS capable for the ac-SECM measurements. The control electronics ensure movement and data collection are synchronized and interfaces all of the electronic components with the control PC. Finally, the optional VCAM is used for probe positioning and experiment setup. As we've already mentioned, the probe is incredibly important for SECM measurements. It controls the final resolution and quality of the measurement. The SECM probe is typically composed as shown. At the top, there is an electrical connection which allows its use as a working electrode. The probe itself has a glass body which seals around the platinum wire. The diameter of the platinum wire is known because this controls the resolution of the measurement. For an SECM experiment, the general rule of thumb is that the probe can detect features up to 10 times smaller than the diameter of the active area of the probe. Detection at this level requires the feature of interest to be well isolated from other features, which otherwise lead to overlap of the diffusion fields and blurring. Typically, a probe similar in size or smaller than the feature of interest would be used for the best images. Notice that the probe is conical at the end. This can be achieved by polishing or pulling depending on the probe. At the end of the cone, the tip is polished flat. The aim is to have a flat tip to achieve the inlaid disc shape of interest. If the active platinum is raised or inset into the probe, the quality of the measurement will be affected. It is important that the probe is polished flat to achieve a well-defined RG ratio, as will be discussed. The RG ratio is the ratio of the insulating sheath of the electrode to the active area of the electrode. This ratio controls how sharp the final measurement is, with the aim to achieve an RG ratio of 10 or less. If the RG ratio is too large, the glass sheath blocks the diffusion of the redox mediator to the active region of the probe too well. This can result in the probe being positioned too far from the sample surface and the measurement having poor sensitivity. If the RG ratio is too small, on the other hand, the signal quality can also be affected. In this case, the redox mediator can diffuse too easily to the probe, which can reduce the negative feedback over an insulator. What sort of results do we expect when a simple test sample is measured by dc-SECM? The results which will be shown were measured on a gold disc embedded in resin in a 0.1 molar KCl, 2.5 millimolar ferrocyanide solution. The 25 micron platinum probe was biased at 0.7 volts while the sample remained unbiased and disconnected from a potentiostat. The first step for any dc-SECM measurement is the measurement of the cyclic voltammetry of the probe. When working with a redox mediator electrolyte system you've not used before, The CV is performed to determine an appropriate bias potential. The aim is to work at a potential which shows diffusion control, which is apparent in the CV by the current plateauing. The potential should also be selected so the current is non-zero. In this case, we could work in any of the regions now highlighted in blue. Even if you know the best potential to work at, a CV should still be run to check the probe quality. If the CV shows lower current than expected, if the shape does not match that shown, if the slope is very shallow, or if there is no signal measured, the probe either needs to be polished or replaced. After running the CV, the probe is approached to the sample. The approach to gold is shown. The probe to sample distance decreases as we move left across the plot. Notice that the current initially starts around 7.5 nanoamps, but as the probe to sample distance decreases, the current increases exponentially to 12.5 nanoamps at the end of the experiment. On the other hand, when we measure the approach to the resin, the current initially starts around 7.5 nanoamps and decays exponentially to around 0.5 nanoamps as the probe to sample distance decreases. Finally, the area map can be performed. In this case, it was measured to cross the gold resin boundary, allowing us to see that the gold disc appears as an area distinct to the resin with much higher current. This is further apparent if we look at an X cross-section of the map. In this case, we should note that as the probe moves across the gold, the current decreases, while it increases across the resin. This is indicative of the sample having some tilt along the X-axis. And what about measurements performed using ac-SECM? In this case, the sample is measured in tap water, a low conductivity electrolyte. A high AC frequency of 50 kHz is applied. The AC bias is 100 millivolts and the DC bias is 0 volts versus OCP. As with the dc-SECM measurement, the sample remains unbiased and is again not connected to a potentiostat. Again, the probe is approached to the sample prior to performing an area scan. The approach to the insulating resin is shown with the impedance seen to increase with decreasing probe to sample distance. When the probe is instead approached to the conductive gold substrate, the impedance decreases exponentially with decreasing probe to sample distance. This is due to the use of a high measurement frequency and low conductivity electrolyte. When the area scan is performed over the gold resin boundary, we can see that the two regions have distinct behavior. On the left, we have the impedance magnitude, which shows a sharp definition between the gold and resin, with the gold having a lower impedance than the resin. With ac-SECM experiments, users have access to a number of map types other than the impedance magnitude, including the AC current magnitude, as shown on the right. Up until now, all of the discussions have focused on constant height SECM experiments. But what happens if you want to follow the sample topography during the measurement? In this case, you need a constant distance SECM technique, which is implemented on the M470 using the intermittent contact, or ic-SECM technique, which we will look at now. We first cover the principles of the technique. There are limits to the applicability of constant height SECM. When a constant height SECM measurement is performed, there is no discrimination between topography and activity effects. Therefore, if a sample with varying activity and conductivity is measured, some interpretation is required. As can be seen in the illustration, an increase in current could be due to the probe moving over a conductor, or it could be due to it moving over a dip in an insulator. For samples like this, data can be difficult to interpret, particularly if the user does not have a visualization of sample topography for a comparison. This issue can be avoided by maintaining the probe to sample distance throughout the scan. When this is done, the topography effect is removed and only the sample activity is measured. This is achieved using the ic-SECM technique, which allows the tip to sample distance to be maintained while measuring separate activity and topography data in a single pass experiment. Unlike some other constant distance techniques, ic-SECM uses a mechanical control mechanism to maintain the probe to sample distance. In ic-SECM, the probe is vibrated perpendicular to the sample in Z at a known frequency and amplitude. When the probe is far from the surface, this is the bulk vibration. When the probe is near to the surface, intermittent contact occurs, causing a reduction in the probe vibration amplitude. This change in amplitude is accurately measured, which allows it to be used as a mechanism to control the probe to sample distance. When the probe reaches a peak, the measured vibration amplitude reduces further, causing the probe to retract until the set IC vibration amplitude is again met. On the other hand, when the probe meets a valley, the measured vibration amplitude is greater than the set IC vibration amplitude. The probe therefore approaches to the surface until the measured IC vibration amplitudes are equal again. The use of ic-SECM is highly advantageous. Unlike standard SECM techniques, the approach to the surface uses mechanical control. Therefore, users don't need to rely on the electrochemical signal, whose strength can vary across a sample, to position the probe. Furthermore, in systems with vanishingly low concentrations of mediator, for example when the probe is far from the surface in generator-collector experiments, the measurement is not reliant on a weak electrochemical signal to find the surface. ic-SECM also has the advantage, unlike other constant distance techniques, that both topography and activity are measured separately but in a single pass experiment. This allows the resulting maps to be directly compared to correlate features and activity. Because probe crash from sample tilt and topography are not a concern in ic-SECM, it is typically performed at smaller probe to sample distances than constant height SECM. This means the signal measured is stronger and sharper when ic-SECM is used. Finally, the mechanical vibration of the probe allows for further data to be measured than in constant height SECM. The probe vibration causes an AC current to form, which is measured along with its phase, giving further information about the conductive nature of the sample. How is ic-SECM implemented on the M470? ic-SECM uses the same basic setup as constant height AC and dc-SECM with the addition of two lock-in amplifiers and a piezo. The lock-in amplifiers provide the sine wave for the oscillation of the probe during the measurement and demodulate the AC signal resulting from this oscillation in order to obtain the signal of interest. The piezo vibrates the probe in a controlled manner in Z. It also performs fine probe positioning when the probe is in intermittent contact with the surface. The use of the strain gauge sensor in combination with the piezo allows the accurate measurement of the change in vibration of the probe, which is required to maintain the probe to sample distance. As with constant height SECM, ic-SECM also makes use of a bipotentiostat with EIS capability, control electronics to interface and control all of the electronics with the PC, and an XYZ scanning stage for precise movement of the probe. The SECM probe used in ic-SECM can also be used in constant height SECM, all of which allows easy transfer between different SECM experiment types. What do results look like for an ic-SECM experiment? The test sample investigated in ic-SECM is the same 5 mm gold sample as investigated in the DC and ac-SECM sections. In this case, the sample is measured in a 5 millimolar Ki, 100 millimolar KCl solution. A 10 micron platinum ultramicroelectrode probe was used with a platinum sheet counter electrode and silver chloride reference electrode. The probe was biased at 0.7 volts, while the sample was at OCP and disconnected from the potentiostat. The probe was vibrated at 455 Hz in bulk with a vibration amplitude of 0.1 microns. We now see the DC current result of the ic-SECM measurement of the gold test sample. Notice the clear distinction between the resin and the gold, with the maximum current difference of over 100 nanoamps. Also notice that there is no apparent tilt in the measurement. When we look at the measurement of the gold sample in the same setup, this time using constant height dc-SECM, the resulting image is very different. While it is clear where the gold and resin are in the area scan, the sample tilt makes the boundary between the two very broad, rather than the sharp distinction we would expect. In this image, we also see the maximum current difference is under 7 nanoamps, due to the cautious positioning of the probe in order to avoid crash. In ic-SECM, the topography map is collected at the same time as the activity map, which is advantageous as it allows the direct comparison between topography and activity features. In many ic-SECM experiments, no tilt correction is performed on the sample prior to the measurement. This means the original topography map often highlights the background tilt rather than the features of interest, as we see here. To correct for this, the map is easily tilt corrected within the measurement software, which in this case results in the map now shown. The ridge where the gold and resin meet can be clearly seen, though overall the sample is seen to be relatively flat. As mentioned, the vibration of the probe results in an AC signal. The resulting AC current magnitude is shown on the left. The gold electrode can clearly be visualized. On the right, we see the resulting AC probe phase. When the probe moves from an insulating to a conducting region, a 180-degree phase shift will be seen, which is unaffected by other factors like the diffusion region around the conductor. This results in a sharp and distinct boundary between the conducting and insulating regions, as is seen at the boundary between the gold and the resin. It is important to note that the strength of these signals is dependent on the vibration amplitude of the probe. In this video, we introduce the different forms of SECM available on the M470. These are dc-SECM, ac-SECM, and ic-SECM. When dc-SECM is used, the probe is biased to interact with a redox mediator. The signal measured in these experiments reflects the local sample activity. If ac-SECM is used, the redox mediator is not required. Instead, a sine wave is applied to the probe to measure the local sample impedance. Finally, ic-SECM can be used with both AC and dc-SECM to perform constant distance measurements. When ic-SECM is used, the sample topography is measured separate to its activity or impedance. Further detail about the different SECM techniques can be found on our website. This includes a variety of application and technical notes, as well as a number of Learning Center articles. Please contact us or your local representative if you have any questions or require further information about any of the SECM techniques covered in this video.